Hello once again, and welcome to the penultimate lesson in this chapter about segment relationships in circles. So, we start out here with some trivia, I guess you'd call it, from 1901. Some divers were down at a Greek island, Antikythera, I guess it's called, and they discovered these interesting artifacts. And these artifacts here were what they picked up, and they used the theorem that we're going to use today, talk about today, to figure out how big the circle was that these were a part of. And these were part of a like a clock that they were used to kind of calculate things about the planets. And this is from 2,000 years ago. And this is what they think the clock kind of looked like back then. And it had moving parts, etc. So they used the theorem that we're going to be using today. Let's move on. So here's the theorem. And the theorem says that if two chords intersect in the interior of a circle, and these are both chords here, CD and AB, if they intersect in the interior of a circle, then the products, the lengths of the segments of the chords are equal. So obviously they intersect each other. So what we're saying is that this part times that part is equal to that part times that part. All right, so that's pretty straightforward. So let's go ahead and get some problems going here. So find the value of x and the length of each chord. So our theorem tells us that, today my pen has been acting up. Let's try it. My theorem tells us that x times the other part of the chord, which is 14, is equal to 7, the other chord's parts, multiplied together. So x is equal to 7 times 10 divided by 14. And I wish we could see my calculator. And that's going to be, it looks like x is equal to 5. So we found the value of x, but they asked us to find the length of each chord then too. So the length of EF, we already know, is 17. And then finally, we now know that the length of HG is 14 plus x, which is 14 plus 5. Is 19. So there's my three answers. They asked us to find x and the length of each chord. All right, the art department is contracted to construct a wooden moon. Here's our wooden moon. One of the artists creates a sketch of what it needs to look like by drawing a chord. Here we go. And its perpendicular bisector right here. Find the diameter of the circle used to draw it. So this is going to be part of a larger moon. Find the diameter of the circle used to draw the outer edge of the moon. So this is the edge right there. Okay? So let's go and we're going to create this. The interesting thing is this is not the center of the circle. Okay? So we're going to call this part over here x. Now, we know these two segments are equal. If the whole thing is 18, that makes that part here 9 and makes that part here 9. Actually, that's fine. Let's go do this. Let's go find x, and then we'll go answer the question. Okay, so our theorem tells us that that part times that part equals that part times that part. So 8 times x equals 9 times 9. X is equal to 81 over 8. And that I don't think reduces to anything. So we found x to be this part. We need to add on 8. Let me take that off. So the diameter is equal to 81 over 8. Plus 8, and we're going to go over here and we're going to type that in. 81 divided by 8, enter, plus 8. And that answer is 18.125, or because I can identify fractions, that's 18 1/8 inches. So we'll send that off to our art department. Moving along here, a secant segment is a segment of a secant with at least one endpoint on the circle. So here we have a secant. It's a line that bisects the circle, or excuse me, intersects the circle in at least 2 points here. So secant segments are starting at N and P and M, and this is another secant, so other secant segments, the segments of the secant are JM and JK. An external secant segment is the part that's on the outside. So both of these here are external secant segments. So our theorem tells us that the entire length of the secant times the part on the outside is going to be equal to the entire length of this secant times the part on the outside. Okay, and that's the way I want you to remember this theorem, using those words instead of all this gobbledygook here. Once again, it's the part of the entire length of the secant and the external segment of that secant. Their product is equal to the product of the entire length of this secant and their external part. And you'll notice these two secants have a shared external endpoint. So let's go apply that now to this problem right here and find the length of each one of these. So the entire length of this secant right here is x plus 8. So we're going to write that down here, x plus 8. And we're going to multiply that by the external part, 8. And then we set that equal to the entire length of this one, which is 16, times the external part, which is 7. I'm going to make my life easier before I get started and divide both sides by 8. And that simply turns this into this. And now my numbers got a lot easier. So it's going to be subtract 8 from 14, and it looks like you get 6. So that's what my x here is, 6. So my entire length of EG is 14, and my entire length of ED is 16. So there once again are my, oh, that was kind of fun. Try that again. And there are my 3 answers for this problem. All right, a tangent segment is a segment of a tangent with one endpoint on the circle. So, tangent segment is from the point on the exterior to the point of tangency. That's a tangent segment, and that's a tangent segment. I believe earlier, too, we learned that these were congruent. That's it. If that's a tangent and that's a tangent, then that part and that part are congruent. We can mark that in there. There you go. But we're going to go play with this theorem here. And it's just a variation of the theorem we learned at the beginning, which is if we have a secant and a tangent, then we have a product. The whole thing and the external part is going to be equal to the whole thing, which happens to be CD, times the external part, which happens to be CD. So you can see it's DC or CD squared. So it's just a little special case of the previous theorem. So let's go ahead and do a problem. So it's the whole thing here, which is 20, times the external part, which is 5, and it's equal to the whole thing, or this thing squared, essentially. So we get 100 equals x squared. X is equal to negative 10 and 10 mathematically, but you know to forget that one, and x is equal to 10. Do we have any units? No units. Gotta love that. All right. So that's the kind of variation on the previous theorem. So that's what we've got today. I wanted to comment here that the moon that we were talking about in the very beginning looks like, to me, like a banana. There it is. I meant to say that. All right. Have a great day, and we'll see you again in Internet land.